if you don't remember what that is, so I'll define it. So let's say, well, I mean, everything we're going to do today actually doesn't really, like usually we work on the first n integers, but actually everything we do today, it's going to not really depend on what the ground set is. So we're actually, let's just make it kind of simple and look at the whole kind of natural numbers. So for f being in here, where k is at least 1, the shadow of f is the set of all, let's say A, in the collection of sets of size k minus 1. So everything in the shadow has size 1 smaller than the stuff in F, such that there exists some B in F where A is a subset, well, of B. Or in other words, you could think of it as all the sets you can get from like A minus some element X, let's say, where A is in F and X is in A. It's probably a more succinct way of writing it. So take the things in A or in F and then delete a point, and that's your shadow, right? Did anyone get a chance to think about this yet? This kind of warm-up problem? Take a bunch of pairs. So this is just kind of think about the case k equals 2. Basically, what we're going to be addressing here is like you have a collection, and you want to say, what's the minimum possible shadow that you can achieve? So this is kind of the simple case where k is 2. So our sets are like, if k is 2, then each set in F just corresponds to like taking 2 points, right? It's kind of like a graph. I don't know. Graph theory maybe wasn't a prerequisite of this, but I mean, if you think about it, if I take the set 1, 2, right? It's just like, you can think of it as this edge, right? Like it's the pair 1, 2. And so you could think of your F as being like, so that would be the set 1, 3 and 4, 5 and whatnot. Maybe 6 is too high of a number to start with, but actually, can anyone get a sense of like, in this case, what is the shadow representing?
For the graph, some the elements in your set F would be kind of like edges. So then the shadow would be the span.
Yeah, it's something like that. I'm not exactly sure what span means, but like,
Or like
it's the things.
vertex that it covers.
Yeah, it's the things that like that are in at least one thing, right? Right. So this simple kind of situation where k is 2. The shadow is, it's all the things you can get by taking a set in your collection and deleting 1 point. That gives you the other point. And so it's just like, if this was my set, my family, the shadow would be this point, this point, like the single element sets consisting of those 5 points, right? So what's the smallest possible shadow if you're allowed to take 6 pairs only? Or if you're taking exactly 6 pairs. Yeah.
7.
It's going to be smaller than that. Are you going to set them somehow by, I don't know, maybe connecting them up like this, or?
Yeah, I guess I was thinking like they all intersect on 1, and then.
Oh, I see. That's another way of kind of get to 7. It would be like something like that. Yeah. You can actually pack them in a bit more tightly than that, actually. You can put over. Yeah, how come?
Okay, 4 is 6 edges.
Yeah, exactly. So here, the answer is going to be 4, right? Because like you can't take 3 points and pack 6 edges into it. Because you can only put 3 edges on 3 points, right? But if you got 4, you can pack all 6 edges into it, right? So yeah, the answer is going to be 4, and the construction is you just take 4 points, you take all the pairs between them. And now, yeah, and I'll tell you that, okay, now you're supposed to take 7 pairs. Like, yeah, it feels kind of unfortunate, like you can almost pack them into 4 points, but now you can't actually do that, so. Yeah, so the answer here is gonna be like 5. And the best you can do is to take like, something like that, for example. And yeah, the shadow is just gonna be all the vertices that are covered by at least 1 edge, right? Okay, we want to try to build some intuition, so I want to solve this for like any possible k. The case k equals 2, it kind of at least points towards some idea that like maybe if you want the shadow to be small, you want to kind of pack all of your sets into like the smallest like set of points that you can or something like that. At least in the case k equals 2, you have to, that is exactly what you have to do. In general, right, kind of intuition is kind of to make the shadow small. It is probably like this is all really kind of hand wavy, but I guess it's probably smart to just not cover that many points, like just to make the union of all the sets in F kind of small. I guess if you start introducing more kind of diversity of different, things in your set, you're probably going to get a more diverse shadow. You're going to get more kind of sets coming up. So yeah, it's probably a good idea to make the small. And actually, in the case k equals 2, when k equals 2, this is actually the only thing you need to do, right? So this is just the answer, right? Just make that as small as possible. Because yeah, anything covered by one of the sets is going to show up as a singleton element in the shadows, right? Things get more complicated though when k is larger, right? So like, I don't know. If I took let's say k is 3, and I take like I want to take a set of size 5 or something. So 5 triples, 5 sets of size 3. Okay, if I was taking 4 sets of size 3, a kind of natural choice is to pick 4 points and take all the, like it's not, I'm kind of not proving that right now that this is the best, but if I was taking 4 triples, it seems probably natural that you might want to just take all the subsets of size 3 from 4 points. When you have to take or actually, sorry, I want to take 6 of these. If I had to take 2 more, like if you think about it, let's say I just want to augment this construction to add 2 more sets, you could kind of do it like this, maybe. So these are the 4 where you've got all 4. I'm just drawing it like this for clarity. Or you could also kind of try to do something like this, where you is it clear that these are different things? So I'm adding, so these, but among these 4 points, just imagine you've got this picture. I just don't want to draw it because you won't be able to see anything that's going on if I draw it. And same with between these 4 points. And then for a 5th point, you could say, okay, I'm going to do this or I'm going to do that. If you think about it, this one's going to be better for making the shadows small because like the shadow, you're first of all going to get everything. So if these are the points 1, 2, 3, and 4, and that's the point 5. You're going to get all of 4 choose 2 in both cases, just from taking subsets of these things. So if this is 1, 2, 3, 4. In this case, you're going to get some sets involving 5. So you're going to get like 1, 5, 2, 5, and 4, 5. In this case, you're going to get one extra thing in your shadow, right? You're going to get, because you can get 5 with anything else. You still get the whole 4 choose 2, and then you can get 5 with 1, 5 with 2, 5 with 3, and 5 with 4. So like this is not a very good strategy, right? What I want to kind of convey here is that, so we try to not introduce new points into the union of the sets, but at some point you're forced to do it because if the size of f is bigger than whatever, something choose k, then let's say L choose k, then I need to cover at least L plus 1 points. And when you kind of cover this extra point, you want to sort of, like if you take this, the sets where you just delete that point and look at these two, you want them to sort of be quite tightly clustered in some sense. Whereas, so in this case, we've got, basically if I drew a graph of all the sets of size 2 that include 5, here they would make this graph, and here they would make this graph. And sort of this one's a better thing. Yeah, so there's some sort of a recursive thing going on here where you want to use as few points as possible, and every time you're forced to use a new point, you want the sets that include that point to not use very many elements as well. But then there's sort of another level of recursion, where among those you want, it's a little bit complicated to sort of get the intuition of this. But yeah. This is all really hand-wavy and rough, but is this kind of building any kind of intuition at all? Okay. Okay, so let me, so it turns out what the best strategy is to take your sets basically according to a certain linear order on n choose k. Where basically this linear order, what it does is it does exactly the strategy we were talking about. It tries to avoid using new elements. And when it does, then among the sets that include that element, it tries to not use new elements within that. When it does, it tries to not use new elements. It's kind of a recursive thing like that. So this is something called collex order, colexographic order. So definition. So let So I'm going to write kind of a curly less than symbol with colex down here. So be a, I guess, a total order, or be the total order on n choose k, defined as follows. So yeah, we want this, if we think about the sets that come early in this order, we want the sets early in the order to be the sets which don't use many elements. So here, well, okay. I'll just write down the kind of definition, and then we'll kind of think about it. So it's defined like this. So if I've got two sets A, where A1, like we write A as little a1 up to little ak, and you can write B as B, little b1 up to little bk, where we think of these elements as being in order. So little a1 is less than little a2, dot, 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 up to little ak. And the b's are in order. Then we say that A is less than B in colex. So colexographic order is the full kind of name for this. If AJ is less than BJ, where J is the largest index, such that these two sets differ. So here I'm kind of implicitly assuming these are different sets, right? I mean, if you have a total order, you can't, it's not reflexive, right? Like A can't be less than A. So yeah, two different sets. We order them this way. If you look at the biggest place where they differ, the last place where they differ, if the element of A is less than the element of B on that last difference. Maybe to get some intuition, let's do some examples. So I guess I've got these two sets, and I want to know which one's bigger in colex order. Which one does the alligator eat? So with this, you've got to like really, so like colex is, we're going to write down, this is kind of related to lexicographic order, but it's like not the same, right? If I was doing lexicographic order, like if we thought of this as a word, like kind of 1, 2, 5, 2, 3, 4, and I said which one comes earlier in the dictionary, it'd be this one, right? Because I look at the 1 and it beats the 2. It's less than the 2, so I just say this one's first, right? But I'm not actually, so that's lexicographic order looks at the lowest thing where they differ. And it says which one's smaller. But this is looking at the highest one where they differ, and they're saying which one's smaller. So, which one of these two things is this one bigger in Lex or colex, or is this one bigger? Yeah, I guess because of the 5, right? So it doesn't really matter that sort of these things kind of in some sense dominate those ones, but that doesn't matter. We just scan from right to left, and we see where's the first time they differ, and we pick the bigger one. So to point the, so that's the bigger one. And then again here, we again kind of go from right to left. We see equal here, so we do nothing. We go to the next thing. That one's bigger. So we go that way. So just a kind of comment that the more familiar lexicographic order, so if I did, so we can also kind of introduce this notation. So this is the same, except we want AJ to be less than BJ for J being the minimum I such that they differ. All right, that's how you do the dictionary usually. You scan from left to right with 2 words. And if they're equal, you don't care, and then you find the difference, and the smaller one goes first, right? But yeah, this is scanning from the right. Does this make sense? So let's see what the first few sets in colex look like. And we'll kind of see that it's kind of following this intuition, this idea of it's trying so hard not to introduce new, big numbers. So if I do my kind of the first sets in, let's say, naturals, choose 3 under colex, colexicographic. I'll write it down properly once. So that's the long way of saying it. So yeah, the first set is kind of unsurprisingly 1, 2, 3, right? So now the next set we can't stay within 1, 2, 3. There's only one there's only one set there. So we have to introduce the number 4. But then subject to using the number 4, we want to make the other 2 elements as small as possible. And so for a while, we're going to use sets that include 4. And we want to keep these ones small, but now I can't keep these ones in 1, 2, so I have to move it to 1, 3. So I have to sort of introduce the number 3 on these sets. And then 2, 3, 4. Now I've got no choice. I've exhausted all the subsets of 1, 2, 3, 4 of size 3. I have to introduce 5. So it's 1, 2, 5, 1, 3, 5, 2. Yeah, I'm sort of tempted to write 1, 4, 5, but that's not right because I want to keep that 3 small. So I write 2, 3, 5, and so on. So Lex order would be totally different, right? Well, it starts the same. But if I take the first sets in Lex order, I'm actually forever going to keep the numbers 1 and 2, right? Because if you imagine you've got an infinite alphabet, and you list all the words, like you would never get past the point where, yeah. These are the first sets in Lex order, and it just keeps going forever, right? Just 1, 2, something. So there's kind of these, yeah. Any questions about this? Yeah.
Is this like meaningfully different than like the definition is you?
Actually, I think that is the same. Yeah, so somehow there is a relationship. Well, okay, I should be careful with this because we're looking at the well, so if I fix my ground set to be like just the numbers 1 up to n, then like to go from colex to lex, yeah,
I guess there's no
So we flip
minimum
the ground
analysis if you have the full set of natural numbers, which maybe matters sometimes.
yeah, well, let's say we're just, working in like, yeah, I don't know, n choose, this kind of n choose 3 thing. There is some kind of relationship between lex and colex where but he said you can try to think of it as switching the ground set backwards, maybe taking complements or something. But I don't know if that's maybe similar to what you're saying, but because if I switch 1 to n, I might get like this. That kind of changes maximums to minimums, right? Something like that works. Yeah. So these are related somewhere. With the naturals, it's kind of awkward because there's no last natural number, so I can't switch it, right? But yeah. Any other questions, thoughts? Okay, so the Kruskal-Katona theorem, which is what we want to prove, determines the maximum size of a shadow of a collection of sets, and it defines it, it determines it in terms of this colex order. So the theorem Kruskal-Katona so for K at least 1, and let's say M at least 1, if F is a subset of naturals choose K, M, then the shadow of F the cardinality of the shadow of F is at least the cardinality of the shadow. I'm going to kind of write this, it's kind of an implicit thing, like, so of the first M sets under colex, whatever those happen to be. So under colex on, like, naturals choose K. So basically, the best way to minimize the shadow is to take sets in order in colex, starting at the beginning. Does this statement make sense? It is kind of like unfortunate that I'm not giving you like a number here, right? Like some function of m. It's like, well, okay, figure out this number, and then that's the bound. But yeah. Okay. So yeah, this is gonna take us a while to prove. So this is going to go on at least till next time, and maybe the class after that. So in order to prove this, we're going to need to analyze this Colex order in some way. Like, we're going to need a better understanding of it. So the first kind of lemma is, so if I give you a set, I want you to like be able to kind of tell me where is that set in Colex order. So if I give you the set 100, 150, 1247, like this will give us a sort of way of computing where does that fit in Colex order. And note that like maybe it's kind of subtle here, right? Like this is gonna, in Colex order, this, like if I list things from the start to the end, that will cover all of the sets, right, of size, which is not the case in Lex order, right? So there's something subtle here that we, like for every set, there is a position of that set in Colex order. It does eventually appear in the list. Whereas in Lex order, that's not even true, but. Okay. So for a set A, which is A1 up to AK, where we list them again in increasing order. So the elements are A1 less than A2 up to AK. The number of sets that come before, so strictly before A in Colex on the naturals choose K is equal to this sum. Sum I equals 1 to K A sub I minus 1, choose I. Maybe we can see that this checks out in this example. Like, this would be like A1 is 1, A2 is 2, A3 is 3. The sum would give me A1 minus 1, choose 1, plus A2 minus 1, choose 2, plus A3 minus 1, choose 3. But this is just like 0, choose 1, 1, choose 2, 2, choose 3. They're all 0. So this is saying for this set, the number of things coming before it, there are none, right? Because it's the first one. This one, I think, would then give you, like, these two numbers are the same. So these are both 0 still. And that'll be 3, choose 3, which is 1, saying that there's one thing before this in Colex. It's that set. This one, I guess at the end you get, well, yeah, so you have 1 minus 1, choose 1, 3 minus 1, choose 2, 4 minus 1, choose 3. That's 0 plus 1 plus 1, because it's 2, choose 2, 3, choose 3. And that's saying there are two things before it in Colex. So like, and this is, if you keep going, you'll see that the formula checks out. Okay. Yeah, so the proof of this lemma is just a bit of counting. So we just have to think of what are all the ways that a set could come before A. And like, basically, that's just kind of saying, I mean, how many of the large elements do those two sets agree on? So, like for example, so any set in AK minus 1, like in square brackets, choose K, for example, comes before A in Colex, right? Those are the sets where, like when I look at the largest index where they differ, it's the last index, because it's like a set in this set, like it doesn't have the element AK in it. So if I look at the kind of highest index, AK, any set in there will differ, like it will not have AK, and it'll have a smaller largest element. The largest element will be smaller than AK, right? So that's where they'll differ, and that's going to determine that that set's less than A in Colex, right? And now I could say, okay, what about the things where they don't differ on AK, they both have AK, and then they differ previously? Like, so by the way, this is giving me the last term of the sum. So the number of such sets right? So the number I've counted so far is that. So kind of a next case to consider is if I have a set of the form S union AK where S is a set of size k minus 1 whose largest element is less than AK minus 1. Then B comes before A. I'm just kind of breaking it down into disjoint cases here. Does this make sense? Because this would be the sets where they share the largest element. And now I look, remember you scan from right to left. So like they share the largest element. I move to the next element. In A, I see AK minus 1. In B, I see a number that's less than AK minus 1. And so that's causing B to come before A, right? And the number of these is A sub K minus 1 minus 1. Choose K minus 1. So these are giving me the kind of correct terms here. Like this is the first one's the case I equals K. The next one's the case I equals K minus 1. And then you just keep on going like this. So yeah, so if I have a set of the form B, let's say equals S union AI plus 1, I plus AI plus 2 up to AK. Where this set S is in square brackets AI minus AI, A sub I minus 1. Choose probably I. Okay, so this would be where they share the first, the last K minus I elements. Yeah, so then this thing comes before A in colex, and there are AI minus 1, choose I of them. So this is just generalizing these first two cases. And then if you think about it, this is counting everything that comes before A is going to get counted exactly once, right? So breaking up cases based on how many large elements they share. So yeah, sum up. Okay, sum up all these things, and then you get the answer, right? Any questions about that? I realize I shouldn't wear such a dark shirt when I'm like using chalk, getting it all over myself. Yeah, so this gives us like a way of computing. Like if I give you a set, you can determine where does it lie in colex order. You know, which position is it? Well, it's saying how many things come before it. So if you just add 1 to that, then it's like if m equals this number plus 1, then A is the mth set in colex, right? Okay, so this gives us a kind of weird corollary that we're kind of going to, in some sense, we're kind of going to use to restate the Kruskal-Katona theorem. This is just a sort of a fact about numbers. Like it's a strange corollary kind of. So for any m, let's say k at least 1 and m at least 1, there is a unique increasing sequence A1 less than A2 up to AK such that m is equal to 1 plus the sum I equals 1 to k, A sub I minus 1, choose I. So yeah, this is just like a fact about numbers, I guess, right? And and these are like an increasing sequence of positive integers, right? Yeah, let's say. So this follows directly from this lemma, because I can just say, just take the mth set in colex. So take the mth set in n naturals, choose k under colex, and let A1, up to AK be its elements. In the correct order, so that's an increasing sequence. And then by the lemma, well, the formula holds because if A is the mth set in colex, there are m minus 1. There should be m minus 1 things that come before it, and m minus 1 is like just this, right? So there, I mean, if if A has these elements, we showed that there are this many things that come before it, and we're saying it's the mth set, so it's like m is this plus 1. So I mean, the formula does hold. And it's also unique because, I mean, the choice of the mth set in colex is unique. So the sequence, so if there's another sequence that had that property, that would also be the mth set in colex, but there's only one mth set in colex. So the mth set in colex is unique. So the A1, so this sequence is unique. Any questions about that? It's kind of a strange thing to be proving, but it's somewhat useful for restating the Kruskal-Katona theorem. So I'm just gonna state two things. I'll state another lemma, and then I'm going to restate the theorem, and maybe we'll prove this lemma next time. So let's see if I can do this in 1 minute. So take an increasing sequence. So yeah. And let m be 1 plus this same sum as usual, ai. Sum of ai minus 1, choose 1. I equals 1 to k. And I want to say that the size of the shadow of the first, oh, I'm out of time, m elements of colex is equal to kind of the same thing, except small difference. So I'm not going to have the 1 anymore. So get rid of the 1, take the same sum, except choose I minus 1 instead of I. Anyway, so maybe I won't restate the Kruskal-Katona theorem, but we'll do that next time. And I'll also prove this next time. All right.